Okay, we're going to continue with the gamma function and sort of provide a bit of a bridge between what we have looked at with power series and what we will be looking ahead to with Laplace transforms. Now, we looked at the gamma function of natural numbers, but let's say that if we were interested in looking at the gamma function of fractions, okay, and a pathway to this type of problem is looking at the determination of an improper integral, specifically where we are looking at the integral of e to the negative x squared dx as x goes from 0 to infinity. Now, there are various pathways that can be taken, and now a common approach is through the use of double integrals. And if we let I be equal to the integral going from negative to positive infinity of e to the negative x squared dx, and we will also have I equal to the integral of e to the negative y squared dy as y goes from negative to positive infinity. And if I were to combine by multiplying, so if I square out I, I'm going to have a double integral, so multiplying these integrals together. So I have a double integral with the limits going from negative to positive infinity. Now we'll have of e to the negative x squared and times e to the negative y squared dy, and putting in compact notation and by the product property of exponents, I have e to the negative x squared minus y squared dx dy. And just looking at it from a schematic standpoint, and we have inserting so you have a rectangle, okay, and we have with the Cartesian coordinate system, okay, we'll say that for this rectangle, okay, which is going to be expanding, we'll say we have for what we have here. Okay, so we have for the area, we have is equal to x times y. And if I take the differential, we have the change in the area is equal to dx times dy. Now, this is what I have in the rectangular coordinate system. Okay, so we have just, in essence, okay, so you have x expanding, y expanding. Now, for what I have over here to make what I have here integrable, I can relate this over to what is going to be in this case, working with the rectangular, going from the rectangular coordinate system to what we have working with radians. Okay, and so for what we have in the crossover. Okay, now we know that with dealing with the polar coordinate system, okay, now we're going to have that x squared plus y squared is equal to r squared. And for what I have here, I have e to the negative x squared minus y squared, and negative x squared minus y squared is equal to negative r squared. And from what we have from a visual standpoint, okay, so going from the cylindrical, I should say going from the Cartesian to what I have in the polar system. And for those of you taking Calculus 3 or who will be taking Calculus 3, you'll be dealing with the cylindrical coordinate system as well as the spherical. And in the case of what we have with the cylindrical and the polar coordinates. Okay, so what we're going to have here is that in translating out, we have as an analog to what we have with the rectangle that was inscribed. So you're still looking at expanding both horizontally and vertically. And now just taking a section, what I have here. So if I take, in this case, a circular sector, and we have that a is equal to 1/2 r squared theta. And I'll write the differential on this. Okay, so we're going to have that change in area. Okay, it's going to be equal to, you have 2 times 1/2. So that's going to be r dr. And we have change in the angle. So we have the differential. So we have dA is equal to r dr d theta. And again, you're going to have this particular circle to be expanding. So we're going to have expanding on out. Okay, all right. Now, in the crossover, and we have upon replacement, we're going to have e to the negative r squared. We have r dr d theta. And for what we have in the layout, now for the radius, okay, so you have other circle. So we have 0 is less than or equal to r, which in turn is going to be approaching infinity. And for what we have in terms of a circle, well, going full circle in the radians, in this case we're going out to 2 pi radians. So taking what I have in the limit, say we have for the inside, okay, so you have r to be going from 0 to infinity. And for theta, I'm going from 0 to 2 pi. So just looking at what we have for the integral, inside integral. And the integral was going to be r times e to the negative r squared dr. And that is going to translate out to, if you think along the lines of substituting, so you have u is equal to negative r squared, du is equal to negative 2r dr, and du over negative 2r is equal to dr. So we have in the integral, so we have r times e, and I have r times e to the u. And for dr, I have du over negative 2r. R's will cancel out. And that's going to be equal to negative 1/2 times e. And once I substitute back, or back substitute, I have negative 1/2 of e to the negative r squared, followed by the constant. So we have with the double integral here, so I'm going from 0 to 2 pi. Antiderivative, so I have negative 1/2 of e to negative r squared. Again, as r goes from 0 to infinity, d theta. All right. And at the upper limit, so we're going to have the negative of infinity. E to the negative infinity goes to 0. And we have with the lower limit 0. So for what I have on the inside, it's going to come out to a positive 1/2. So I have going from 0 to 2 pi. Then we have of 1/2 of d theta. And for the antiderivative, okay, so that will come out to 1/2 of theta. This theta goes from 0 to 2 pi. And for the end result here, okay, so this will come out to pi. So we have, in this particular case, all right, so we have I squared is equal to pi. Now again, what we had I to represent, okay, so you have I is going to be equal to the square root of pi. Again, we had I going from negative to positive infinity of e to the negative x squared dx, which is equal to the square root of pi. Now, we have with e to the negative x squared dx. Now, this is an even function, and you'll have a symmetry with respect to the y-axis. So it's going to follow that we're looking at half of this particular region. So we're going to have that the integral as x goes from 0 to infinity of e to the negative x squared dx is equal to the square root of pi all over 2.